So far, we've focused on the simplest atom, hydrogen, which has one proton. So it has a charge of +1 in the nucleus, and neutral hydrogen then has one electron. And that one electron is attracted to the nucleus because the nucleus is positive and the electron is negative. And a plus-minus attraction is what keeps the electron close to the nucleus and confines the electron to the nucleus, making the energies quantized. If we go to the next most complicated atom, so if we go to helium, now we have two protons and perhaps some neutrons in the nucleus. So we have a 2+ charge. So we have a higher positive charge, so 2 protons. And that means that we also have 2 electrons in the neutral helium atom. So we have 2 electrons that are around our nucleus that has a +2 charge. Now, what's going to happen here is that we are going to have a plus-minus attraction between this electron in the nucleus and between this electron in the nucleus. So both electrons are going to be attracted to the nucleus, but they're going to be attracted to a +2 charge, so they're going to be attracted more strongly than the electron in hydrogen is to its nucleus. However, we also have this other force that is occurring in this atom, and that is an electron-electron repulsion, because both of these have the same charge, and so they repel each other. So we have an attraction and we have a repulsion. Now, the key here is that attractive energies, or attractive forces, lower the energy of the system. So the stronger the attractive force, the more the energy gets lowered. But repulsive forces actually raise the energy of the system. So we have a push-pull thing going on here where this positive negative attraction for each of the electrons lowers the energy of the helium atom relative to the hydrogen atom. But then this electron-electron repulsion is going to raise the energy a little bit more than what you would expect, just because if you didn't take into account the repulsion and only took into account the attractions. So the effect of this electron-electron repulsion means that the energy levels for many electron atoms are a little bit more complicated than for hydrogen. So remember, for hydrogen, we started with n equals 1, and then we had n equals 2, and then we had n equals 3, and then we had n equals 4, and all we had to worry about was what n level we were in. We didn't have to worry about what the shape of that orbital was, so what the L quantum number was. But for atoms that have more than one electron, such as helium, where we have this electron-electron repulsion, the shape of the orbital is going to interact differently with different electrons in levels with different shapes. And so the amount of repulsion is going to change depending on the L quantum number. And so we have a much more complicated atomic energy level diagram, where we have our 1s, and then we have our 2s, but the 2p is a little bit higher in energy than that because its shape is slightly different, and so the electron-electron repulsion is stronger, and that raises the energy a little bit more. And then we have 3s, and then we have 3p, and then we have 4s, and then the 3d sneaks in here, and so forth and so on. So it gets pretty complicated how to figure out what order the the orbitals are in terms of their energy levels. So we have a mnemonic to help us remember what the order of those energy levels are. And remember that the reason that not all the n equals 2 levels are the same is because they have different shapes, and so the electron-electron repulsion is different when I'm in a spherical shape than when I'm in a dumbbell shape. And that raises the dumbbell shape up a little bit higher in energy than the spherical shape. Same thing for the clover shape, gets up a little bit higher than the dumbbell because of the shape of that orbital. And so now the energies depend on both N and L rather than just on N, which is what was happening with the hydrogen atom where we have no electron-electron repulsion. So there are a couple of ways that you can use to remember the order in which the orbitals go in terms of energy. So if you put the N levels from lowest to highest in a column, and then beside each N level you put the possible different L quantum numbers that you can get for each of those N levels. Then you use diagonal arrows starting at the lowest energy level, 1s, and then go 2s, and then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, etc. You can remember the order in which the energy levels are in that energy level diagram for many electron atoms. Alternatively, and the way that I like to think about it, is in terms of the periodic table. So in the periodic table, each of the rows represents a different n level. So this first row is n equals 1, then we have n equals 2, then we have n equals 3, then we have n equals 4, then we have n equals 5, n equals 6, and n equals 7. So these first two columns are elements that fill and that have their final electrons in the ns shells, subshells. So what we have here is that if we're in row 1, then the outermost electron is in the 1s orbital for the lowest energy of the atom. And so if we go to helium, then the electron is still in the n equals 1s orbital. For n equals 2, now lithium has its outermost electron in n equals 2s, beryllium also 2s. Now what happens when we come over here, these elements here, these 6 elements here fill the n equals or np subshell. So if I'm in row 2, row 1 doesn't have any p orbitals, but if I'm in row 2, now my outermost electrons, the next electrons, are in 2p. So these all 6 of these atoms have electrons in 2p in their lowest energy. And then if I move to n equals 3, these are the n3s. These two atoms have electrons, outermost electrons in 3s. These are 3p. Now when I go down to row 4, what's going to happen is that I still have my 4s, but now these 10 elements fill the n minus 1d. So I go 4s, 3d, because 4 minus 1 is 3, 3d, and now I'm back to 4p. So 5s, 4d, 5p, and then 6s, and then what happens is this gets inserted in here, right? So these guys fill the n minus 2f orbitals. And so we go 6s, 6 minus 2 is 4, 4f, 5d, and then back to 6p. 7s, 7 minus 2 is 5, 5f, 4d, and then there aren't any other elements that we know. So if you can think about the periodic table this way, that's going to help you remember. So we go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, and then we don't have any more elements. So the advantage of using the periodic table as opposed to this mnemonic device is that then you're also going to always be able to write the electron configurations, which is the next thing we're going to talk about for each of the elements, because simply by knowing where they are in the periodic table, you'll know what electrons to put where based on where they are in the periodic table.